It is time for a very exciting topic, the chain rule. So what is the chain rule? The chain rule is an invaluable tool that you need to take the derivatives of functions within other functions. So consider f of g of x. So the idea here is that you've got one function inside of another function, very common in math. What we want to know is what's the derivative of f of g of x. Certainly, it's the derivative of your function, which is f prime of g of x. But that's not all, because we've got this other function that we also need to take into account. Right? If we're looking at how is the overall function changing when you change x by a little bit, certainly g is influencing that. And the way you account for that influence is you multiply by g prime of x. Okay? That is the chain rule in action. Okay, let's take a look at it in terms of an example. Okay, so consider, for instance, let's take the, we're going to take the derivative. So we'll have a d dx, right? Derivative of what? Let's go with the sine of x squared. Okay, so what's the derivative of the sine of x squared? Well, we know that the derivative of the sine of x is in fact the cosine of x. So we need that, okay? Cosine of what? It's cosine of whatever's inside. Now it's not just x here, it's x squared. So it's cosine of x squared. But by the chain rule, we must also take the derivative of the inside function. And we do that via multiplication. So this is going to be times 2 of x. Okay? Once again, when we're looking at what is the change, how does the function change when x changes by a tiny amount? Well, certainly it's not just sine of x, right? It's changing by a square, and so we have to include that. Okay, let's look at a similar example. What if we look at, let's just do another straight derivative, d dx, used to this operator notation. What if we do this of the sine squared of x? Okay, what does this equal? Now, you have to be aware of the difference of these two, okay? And so, this one's clear, it's the sine of just the square of x, but this is the sine of x, the whole thing squared, okay? You don't put the square at the end because it can be a little ambiguous. So this is taking all of sine of x and squaring it. Okay, so if you're taking the derivative, your outside function is something squared. And so how do you take the derivative of something squared? You bring the 2 down and multiply by it just up here. So that's the first thing. That's the outside function. It's 2 times the sine of x. Okay? Right? That's what we squared, 2 times that. But by the chain rule, you've got to multiply by the derivative of sine of x. So it's times cosine of x. Okay? The chain rule is really going to widen the examples that you can do for taking the derivative. Okay? It really opens things up. So let's go over a couple more examples. Okay? Consider the following. Consider y equals what? How about e to the x squared plus, let's go with the cosine of 2x. Okay, so this is interesting. So what we want to know is what's the derivative of this y. Okay, and preparation of some things coming, let's use Leibniz notation. So we want to know what's dy dx, same as y prime. Okay, so we've got e on the outside, we've got e to something, right? It's not just e to the x. So, like, we would like this to be, oh, the derivative is just e to the x squared plus cosine of 2x, but certainly what is in the numerator, right, the x, not the numerator, the exponent, the x squared plus cosine 2x matters. You can't just ignore it. Okay, that's the whole point of the chain rule. the way I think of the chain rule is you take the derivative of everything, okay? And it's always multiplication. So this is going to be times simply the derivative of this piece. Well, the 2x is going to be, sorry, the x squared, the derivative is 2x. And then, now be a little careful here because when you do the plus, it is going to be a plus. Okay, derivative of cosine and sine is going to be a minus, but it's e times this whole thing. It's not e times 2x and then an extra minus. So this should all be in parentheses, right? So derivative of cosine is negative sine. So it's sine of 2x. And you should ask yourself, okay, am I finished? And the way you know with the chain rules, had you taken the derivative of everything, okay, we did e, that's giving the same thing. We did x squared, that's the 2x. We did the cosine, that's the negative sine, but we have not taken the derivative of the 2x. And so that is going to be also times 2. Okay? There's the derivative of that function. Okay, let's do another one. Let's go with y equals, and it's going to be a fun one. At least I think so. You might not. Sine of the sine of the sine of x. Let's say theta. Change up the variable. Okay, so we have like a triple nested function here. So how do you tackle this using the chain rule? What you do is you start on the outside and you work your way in. Okay? And you've got to be careful in this one. Go one step at a time. Now our variable here is theta. Okay, so if we're using the Leibniz notation, wouldn't be dy dx here, it would be dy d theta. And what's this going to equal? We start on the outside, we get, it's the cosine. Right, the derivative of sine is cosine of what? It's of whatever's inside. So what's inside here is the sine of theta. And, okay, that's like our first step. Now you must take the derivative of the inside, which is this piece. The sine of theta. Okay, the derivative of that piece is simply the cosine of the sine of theta. So it's going to be cosine of the sine of theta. And then finally, you're going to have one more chain, right? The chain rule, right? It's a chain of derivatives because we have to take the derivative of this sine of theta, which is one more cosine of theta. So it's times another cosine of theta. So that is dy d theta for that nested function. Okay, chain rule I think is cool, it's fun, it's probably the most useful tool of them all when you're learning how to take derivatives. Because it's very common that you have to work with, nested functions. And you also have to think about them carefully. You have to know the difference between like a function within another function and, multiplication, right? This is not sine times something, right? Like if we had, for instance, let's say y equals sine theta times cosine theta, there's no chain rule here. This is not like one function inside of another. This is the product rule. You're just multiplying two together. Since we wrote it out, let's go ahead and do it. We'll use the y prime notation this time. Derivative of the first is cosine of theta. And what's cool is cosine of theta times cosine of theta would actually be cosine squared theta plus sine times the derivative of the second. The derivative of the second will be negative sine, so we end up with a negative sine squared theta. Okay, so you get that after you multiply out the like terms. Pretty cool. Now, I do want to go over one more piece. Okay, let's just look at a simple one here. And let's consider something a little more easier than this one. Let's just look at y equals e to the x squared. And what we're going to do here is we're going to do a change of variable. Okay, so what's our change of variable going to be? What we're going to do, we are going to let u equal x squared. Now if we do this, we get the following. We get y equals e to the u. Okay, So what's the derivative? Okay, well this is interesting. What notation should we use? That's another interesting question for this one in particular. And it might be useful to look at both. So if we start with just y prime, we can say, well, that's just e to the u, right? Like the derivative of e to the u is just e to the u, okay? But u is x squared, right? And we started with u as x squared. So suddenly this notation becomes a little problematic, right? What I'm saying here is if you ignore the derivative, if you start with y equals e to the u, derivative of y prime is just e to the u. But if you equal something else, oh, that's a little bit of an issue. So what do we do here? Well, what if we look at the different notation and we say, okay, let's say dy equals eu, and then what's this other notation? We've had dy over du, right? Okay, so if you have dy over du, it's almost like if you multiply both sides and you get du on the right side, okay? Okay, so this is accurate now, but what's du? We'll look up here. The idea, we haven't done this yet, is that when you take a derivative, you can always write the d, okay? So if we take it, now just start here. If you take the derivative of u, it's du. What's the derivative of x squared? It's 2x, but then you put a dx here, okay? So whenever you take a derivative, you can put a du and a dx, and that's where sort of the notation du dx equals 2x comes from. But when you look at it here, in the context of this problem, it says, and what we want to say here is you want to substitute this in. We want to say dy equals e to the u, okay? But what's u? U is x squared. So if you substitute in x squared, du, and what's du? It's 2x dx. And certainly this implies dy dx equals e to the x squared 2x, which is the chain rule in action, okay? So this y prime isn't as good of a notation when you're using the chain rule. The d's are actually much more helpful, because going from here to here is absolutely true, right? It's just in terms of u. dy du is e to the u. But if we want it in terms of x, you've got to go back and make a substitution. And you've got to say what du is, okay? Now I realize the style of the derivative at the end, using du's and dx's, is new for most of you. And you will get plenty of practice with it because there is a later technique called implicit differentiation that we will look at soon that actually uses this. But just to recap, significantly, for the chain rule, you need to take the derivative of every piece. So if you have a function, you want to take the derivative of the whole thing, you can't leave out individual pieces. Like up here, I can't ignore the 2x. Any connection to x, you must take the derivative of it, and you chain it together through multiplication, okay? Chain rule definitely takes practice, it definitely takes getting used to, but always take the derivative of every piece. Remember to multiply, and you can't go wrong.